Pluto is a distant and mysterious dwarf planet that was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets that could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms alpha libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a phenomenon called alpha libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, Bond, Zippel, Leo, and Kai, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems all over the place, this oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even if things in space seem wild and random, some patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, making sure it doesn't crash into Neptune or get thrown off course. This three-body problem helps in understanding how these paths change because of the way these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, and Saturn helps a bit too. These tests show that Jupiter's gravity alone is strong enough to make sure Pluto stays on a stable path for a really long time, even billions of years. So it's like Neptune, Jupiter, and Saturn are all working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is really important. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term trajectory. In the vast expanse of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its composition and behavior. One of the most fascinating features of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided unprecedented data about this distant world. The surface of Pluto is characterized by large plains, towering mountains, and deep valleys. One of the most notable features is the Sputnik planitia, a vast, heart-shaped plain that is primarily composed of nitrogen ice. This area showcases a diverse array of geological features, including large icebergs and what appear to be flowing glaciers. The presence of these features indicates that Pluto may still be geologically active, despite its great distance from the Sun and low temperatures. Another intriguing aspect of Pluto is its atmosphere, composed mainly of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin, yet it exhibits fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the intricate relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply rotating around Charon. This unique relationship contributes to the intricate gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, providing scientists with a glimpse into its formation. Pluto's orbital characteristics might offer insights into the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a crucial role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is the potential impact on our comprehension of the solar system's evolution. The gravitational influences from nearby giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can result in shifts in orbits, potentially leading to collisions or ejections from the solar system. As researchers continue to explore the nuances of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the galaxy. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, igniting debates about what constitutes a planet. The International Astronomical Union's definition focused on criteria such as orbital dominance and size, leaving many to ponder the implications of such classifications. This ongoing dialogue reflects our evolving understanding of the universe and highlights the need for a flexible approach to categorizing celestial bodies. Moreover, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, scientists envision sending additional spacecraft to study not only Pluto but also other distant objects that share its orbital characteristics. Such missions could provide valuable data about the primordial materials that shaped our solar system, potentially offering clues to the origins of life on Earth. The role of exoplanets, or planets beyond our solar system, is another fascinating area of study that intersects with our understanding of Pluto. As astronomers discover a growing number of exoplanets, particularly in the habitable zones of their stars, the lessons learned from studying our own solar system can inform theories about planetary formation and habitability. The conditions that allow for stable orbits, atmospheric retention, and geological activity could provide insights into the potential for life elsewhere in the universe. Finally, public interest in Pluto has persisted, fueled by its enigmatic status and the stunning images sent back by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its region of space, we are reminded of the endless wonders that the universe has to offer. Pluto's unique characteristics extend beyond its physical properties and orbit. It also serves as a critical case study for understanding planetary formation and the dynamics of celestial bodies. The formation of Pluto is believed to have occurred in the early solar system, alongside other Kuiper Belt objects. Studying its composition can shed light on the conditions prevalent during the solar system's infancy, potentially informing theories about the formation of terrestrial planets, including Earth. Recent research suggests that Pluto may have a subsurface ocean, a finding that could alter our understanding of its geology and potential for hosting life. Data from the New Horizons mission indicated that some areas of Pluto's surface, such as the icy mountains, may be composed of water ice, which behaves differently than typical rock under low temperatures. This discovery invites further exploration into the possibility of liquid water existing beneath its icy crust, raising intriguing questions about the potential for life, even in such extreme environments. Additionally, Pluto's interaction with its environment can provide insights into atmospheric science. The seasonal changes in its thin atmosphere offer a natural laboratory for studying atmospheric dynamics on a planetary scale. Scientists are particularly interested in how the interplay between solar radiation and the surface can lead to complex weather patterns, akin to those observed on larger planets. The importance of ongoing surveillance of Pluto and other similar celestial bodies cannot be overstated. As more missions are planned, such as those targeting the further reaches of the Kuiper Belt, we can expect a wealth of new information that challenges existing theories and expands our understanding of planetary science. Each discovery adds another piece to the puzzle of our solar system's history and the processes that govern its evolution. Through these investigations, Pluto remains a symbol of the continuous quest for knowledge about our universe, inviting both scientists and enthusiasts alike to ponder the mysteries that lie beyond our earthly realm.